We're gonna discuss today feedback amplifiers. Today we're gonna discuss them kind of in a general context, not specifically for any particular amplifier configuration. And then once we establish the basics of, compensation, lead compensation, and we'll look at how to apply those ideas to specific amplifiers like the single stage op amp and two-stage op amps that are the top of your assignment. Okay. So some of this may be a little bit of review, but I have sometimes I have a little different way of presenting it that can be useful for some people. So it never hurts to get a little different perspective. And also, there's just a bit of establishing notation too. So you're probably familiar with this picture of negative feedback, where there's an amplifier with a forward gain of A, and then a feedback network with response B, or beta. We define the loop gain. So this is a bit of naming we have to be careful. The loop gain, or also called the open loop gain, or more appropriately, the loop response, or open loop response, because of course in general it's frequency dependent. That is what you get by going around the loop, right? So in this picture, that's simply A times beta. And that's just different from the closed loop gain, which is with the feedback loop closed, the response from U to Y. So the notation we're going to use is just a uppercase A is the open loop response of the amplifier alone, whereas A with a subscript CL is the overall closed loop response of the amplifier U to Y. And so, written in this form, right, this is probably a familiar expression to you. You've got the closed loop gain is A over 1 plus A beta, and then we can rewrite that in terms of L, A over 1 plus L, the loop gain. So that's all familiar, but a couple, things I want to point out. The reason I present it a little differently here is because I think in a lot of practical circuits it can be difficult to distinguish between A and beta. Beta is often a very significant part of the load of the amplifier, and so as such it has a big impact on the response of A. So it's kind of hard sometimes to really determine separately, let's say A and beta, because if you take away beta, for example, A changes, right? But the loop gain, or open loop gain, L, is unique, and it's usually there's a very specific prescription for figuring out what that is. Break the loop, you inject the test signal, you look at the signal that comes back. It's unique, right? There's not multiple different ways to define it. The amplifier, you can kind of slice and dice the loop in lots of different ways and define A a little differently, as long as beta takes that into account, and beta, can compensate. But L, there's only one correct L, right, for a given feedback amplifier, and it's easy to find, especially in simulation. So I try and write things in terms of L, right? So that's what I've done here, right? I put L in the denominator, and we're gonna further simplify this a little bit. So in the case where the amplifier gain A gets very large, typical case, then you have a closed loop gain that approaches A over L, or simply 1 over beta. So this I'm going to refer to as the desired gain, or the ideal gain, if you like. It's the gain that you would expect if the amplifier was ideal, if it had a really high gain. It's usually the gain that you're kind of after, that you're trying to achieve with the design. And then the term in the denominator here, 1 plus L, is sort of an error term, right? That takes you away from that, the 1 plus part. So there's just to put some numbers to it, there's an example 5.1 from the book where the amplifier gain A is 80 dB, beta is 0.2. So the beta of 0.2, that's the feedback factor. Your desired gain, let's call it I'm gonna call it A ideal, I'm going to try and call it that, okay? You would expect that the desired gain here is 5, right? 1 over beta. But in fact, because of the finite gain A, then you end up with a true closed loop gain that's a little bit less than that, but very, very close because A is 10 to the 4. Okay. So it gets a little bit confusing. There's some cases, and specifically a very common important case, which is the inverting amplifier, where the desired gain you're after is not exactly 1 over the feedback factor, not in the way we usually talk about the feedback factor anyway. So that gets a little bit confusing. So instead of calling it, thinking about it necessarily as 1 over beta, sometimes, it'll be better to instead consider this quantity as just the desired gain, because that's something that even without doing a bunch of analysis or simulations. That's, again, that's something that just by inspection, you have a feel for it. Just by, this is an inverting configuration, so therefore you expect the gain to be negative Z2 over Z1, for example, right? So gain sensitivity, right, describes how sensitive the closed loop gain or response is to small changes in the amplifier response A. So when the loop gain's really big, then basically the overall gain is inversely proportional to the gain of the feedback circuit, right, 1 over beta, and it's very insensitive to the gain of the amplifier A. So we already saw that in the last case, right, the 80 dB case. It was very, very close to the ideal result. So here's just an expression that shows how insensitive it is. So the key point here is that you see that the change in the closed loop gain that results from a small change in the amplifier gain A is divided by this factor here, 1 plus L squared. Right? So there's a squared there. That means if L is very large, that this term is going to become small very, very quickly. So when the amplifier gain A decreases by an order of magnitude, the closed loop gain changes by less than 0.5%. Okay, that's the example from before where A was 80 dB. Okay. So it's a key point there, right? As always with feedback, the main thing with the amplifier itself is usually not that we have a precise gain, but that we just have a lot of gain. Okay, and we're gonna trade that off for precision. So here's a picture of that's a couple of different magnitude responses plotted on top of each other. So here's where the notation, it's important to keep the notation straight. So this is, I'll label it properly here, magnitude responses. Okay, obviously versus frequency. And so the top curve here is A, the amplifier on its own. And so typically, as I just said, it's got a really high DC gain and has some finite bandwidth. Okay. Now when we go and connect that in the feedback configuration, here's our desired gain. Okay. So if we draw this dashed line here at the level of the desired gain, or 1 over beta, right? Then what we get in the distance between these two, assuming this is a log scale on the y-axis, the distance between those two is actually L, right? So because we've got the 1 over beta there, so when we take A minus that curve, this dashed line here, then it's like taking, because it's a log scale in dB, it's the same as taking A times beta instead of A times 1 over beta, because we're taking the top line minus the bottom line there. So that distance is really a plot of L versus frequency, which means that at the point where those two lines intersect, that's the frequency where we see that the loop gain becomes unity. L becomes unity. I should put magnitude here. Okay. So we're going to often define that the unity gain frequency. We'll see later, right? We'll define this the unity gain frequency of the loop, omega t. And what you also see is that, going back to our discussion over here, right, we saw that as long as the loop gain was much greater than 1, which is usually achieved by having a really big amplifier gain, then we had a closed loop response that was very close to the desired response. So if we look back on this picture, now we've got a loop response, or loop gain L, that's a function of frequency. But at all the frequencies where we have L much bigger than 0, so everywhere, let's say in this part of the curve, then we have a closed loop response, ACL, that's very close to the desired value. As soon as L drops, though, to around omega t, the unity gain frequency, here, by definition, L is only equal to 1. So at that point, we're no longer, obviously, satisfying this criteria, L much greater than 1, which means the closed loop response is no longer equal to its desired value. And if we go further, to higher frequencies, L becomes even smaller. So when we go to those very high frequencies where L is a lot less than 1, then notice what happens to the expression for the closed loop gain. Right? The L term becomes negligible compared to unity, so the closed loop response becomes approximately just the amplifier response A. Okay. So that's why you see this picture here. We plotted this bottom black line is the closed loop response A. So at frequencies where L is greater than 1, it follows the ideal or desired gain. And then once we get to the unity gain frequency, instead it starts following the amplifier A response. So it's very nice graphical way to interpret and estimate things about the closed loop response. So this is just a cartoon sketch for now, and there's one notable sort of assumption that's being made here that's not quite right. We're basically neglecting the phase response of everything, right? We're just saying that 1 plus L, is kind of the magnitude of 1 plus L is the same as the magnitude of 1 plus the magnitude of L, right? Which is in the denominator of ACL, which is not quite right. Later on, we'll see that it depends on the phase shift of L. In particular, the shape of the closed loop response, ACL, in the vicinity of the unity gain frequency, right, will depend on the phase of L there. Because both L and the unity term are about the same size, so the way they add together will depend on the phase of the relative phase of those two terms, right, in the denominator. But for now, let's just go with this. And we'll modify the picture later to take that into account. And you can get, because the reason we're going to go with it, because it gives you really important, useful intuitions. So right away, the bandwidth of the closed loop amplifier is quite related to, pretty much very similar to the unity gain frequency of the loop L. So that's the unity gain frequency of L, not to be confused with the unity gain frequency of the amplifier A. Right? Notice the unity gain frequency of the amplifier A is way over here. We're going to refer to that later as omega t A. We're trying to stay consistent with the notation. But that may get confusing, okay? Particularly because whenever you have a unity gain feedback configuration, beta equals 1, the two become the same, and which is not an unimportant case. It's kind of a common case. So sometimes the two are the same, the two are coincident, basically when you've got beta equals 1. But if beta is not equal to unity, then the two are different. So omega t, another reason it gets confusing is because, for example, if you look at a discrete op-amp data sheet, it'll refer to ft or omega t just as the amplifier itself. But then, of course, if you connect it to a feedback network, the omega t of the loop is different than what's being reported there, right? So what's relevant in determining the closed loop bandwidth, though, is omega t of L. That's the main point I want to get across. And don't forget that, which means that the bandwidth of the closed loop amplifier depends on the feedback you connect around it. Unless you go and change something about the design of the amplifier itself. All right, we'll talk about that later too. So another important point, so that's got to do with the bandwidth of feedback amplifiers. And another interesting reason why we use feedback, another interesting advantage of feedback is linearity. So to see that, right, you should recognize that with feedback, an amplifier is exposed to signals that are approximately L times smaller than would be the case without feedback. So looking back here at this picture, right, we often talk about this relationship here, the response from U to Y, the input to the output of the closed loop amplifier. But we can also write the response from U to X pretty straightforwardly. So X over U is just 1 over 1 plus L. So as long as L is large, basically got 1 over L. As long as L is much bigger than unity. Okay. So that means that the input to the amplifier, let's say the input to the amplifier has an amplitude of 1 volt, but the amplitude of X is 1 over L times the volt. So if the loop gain is 60 dB, let's say, then that means X is going to be only 1 millivolt, even though the input to the feedback system is 1 volt. This is really important because the amplifier A over here is only seeing X. It's not seeing U at its input. And it's really easy to make a circuit that's linear for 1 millivolt input. Everything is linear if you look at a small enough signal, right? And in particular, because A is the circuit that's providing gain, the only way we're going to get gain is by using active components, transistors. We can't get gain from just resistors and capacitors. So there's going to have to be transistors in A, which means it's for sure going to be nonlinear for large enough inputs. So this is a great way to use those active components. We use the active components to get us gain, and we wrap feedback around it because the gain is not very well controlled, and also because the gain is very nonlinear. But it's okay, the feedback takes care of that. It ensures that the amplifier A only sees a really tiny signal. Okay. So again, all of that valid as long as L is big. If the loop gain for any reason should drop, for example, if there's high frequency signals and L is no longer big, then the amplifier is exposed to that signal directly. May or may not be a problem because at those high frequencies, the amplifier presumably, that the reason L is rolled off is because the gain of A is also rolled off. So it's basically the amplifier is not working anymore at that high frequency. So it may be okay if that's the reason why L is rolling off. Okay. So here, a little bit more about the desired gain. In this expression, it's a clear way to rewrite the closed loop response in terms of only L, right? So this portion of the expression here is only in terms of L. And as I said, L is unique. It's kind of easy and prescriptive to find L. So that's nice. This term here kind of tells us everything we need to know about the frequency response of A, or the frequency behavior of A. All the frequency dependence is baked into this L over 1 plus L, right? We can find out about stability, the gain sensitivity, all that good stuff. And then this term over here is basically the desired gain, or ideal closed loop gain. And that is something that, as I say, usually is sort of trivial. We just know it by inspection. We know, for example, and again, this is why this is an example over here of why I prefer to think of it as the ideal gain. Because here we've got a simple inverting configuration, right? Where we know that if the op amp were ideal, we would just have a gain of negative Z2 over Z1. We don't have to do a bunch of analysis to figure that out. So that's not usually how we define the feedback factor beta, but without basically you can recast the model using Norton equivalence, and you can redo everything so that there's a kind of a 1 over beta that's related to Z2 over Z1. But rather than doing all that, I'm saying, we save ourselves all that sort of mathematical gymnastics and just say, I know the closed loop response is going to be whatever it's supposed to be over here times L over 1 plus L, right? I think that's actually a very practical way. When you talk to practicing designers that have been doing this sort of thing for a long time, they rarely talk about, okay, this is A and this is beta, because it's inherently kind of confusing, I think. It can be ambiguous for a given circuit. But L, the loop gain, is something you always use and that you constantly talk about. I mean, you break the loop, you simulate the response, you look for phase margin and stability and things like that. These are the main tools that we have for analysis of feedback amplifiers. And so I think it's better to focus on L and then a basic understanding of what the desired gain should be. If you want to be specific and rigorous about it, if there's any uncertainty in your mind as to what the ideal gain is, the closed loop amplifier, just think about what the analysis would look like if L became infinity, or if the amplifier gain the open loop gain became infinity. Then that should lead you to the answer of what the ideal or desired gain is. It's sort of, the result you would get from a second-year undergrad analysis, right? So the amplifier's closed-loop gain depends basically only on the desired gain. Again, instead of 1 plus beta, I think it's even simpler to just replace that in your mind with the ideal or desired closed-loop gain times L over 1 plus L. So again, everything we care about, all the dynamic behavior that we care about, the bandwidth, phase margin of the closed-loop amplifier can be obtained from knowledge of the desired gain and the loop gain L. So how do we find L? I sort of alluded to this quickly already. But just to lay it out specifically, first we set all the independent sources in the circuit to 0. So I think that's a good way to write it, because when you think of setting a voltage source to 0, what does that mean? It means like taking this and replacing it with just a wire, right? So it's short-circuiting all the voltage sources. If you have a current source and you set that current source to 0, an ideal current source with a current of 0 means that that current source is like forbidding any current from flowing through it. So that's just an open circuit, right? So that's why I think this statement captures all. Sometimes people get confused. Oh, do I short the voltage sources or the current sources, or right? You just set them to 0. The second step here is you break the loop and you terminate it with an appropriate impedance. So this is probably the trickiest part, especially this idea of terminating it with the appropriate impedance. So in principle, you can break a loop anywhere, right? And this process, if you do it properly, this process will yield L. The problem is that some places, breaking the loop in certain places makes it very difficult to terminate the loop properly. You want to terminate the loop without affecting it, in a sense, right? So usually there's 1 or 2 places where it's a little bit easier to do that. It's a little bit easier to break the loop and still terminate it with the appropriate impedance. For example, maybe there's a node where there's just very, very high impedance, right? There's almost, there's very little capacitance, very little resistance. between that node and ground. So you can just kind of break the loop there and leave it open, and you're pretty close to the right answer because it's a really high impedance node. That's one example. But, you know, really to be accurate, you should always try and include even whatever finite parasitic capacitances or whatever are there. Even if it looks like it's a high impedance node, you should try and include all that, all those small impedances there. So, and we'll talk a little bit about some practical ways to do that in simulation. So then you insert the test signal and measure the resulting return signal. So just to be clear, right, in this picture here, we broke the loop here. I'm showing in general like a differential signal path, but in a lot of cases, one of those two is ground, right? It can just be presumed to be ground, but just to be totally general, there's a differential signal path here. And you can you're looking at the impedance, looking in here, ZT. You'd have to find that either by inspection, or, you know, if you have to, then you do some more rigorous test to figure out what that impedance is, and you connect that same impedance over here. And it may be complex valued in a function of frequency. So often there'll be a capacitance and a small signal resistance part. So they both need to be there. And then the test signal that you inject can be either a voltage or a current. Okay, it doesn't. There's no problem either way. If you do things properly, you will get the right answer either way. If you inject the voltage test signal, though, you look at the returned voltage, VR. If you inject a test current, you should look at the returned current. But obviously you don't want to inject the test voltage and look at the returned current, because then, you know, we know that L has to be dimensionless, right? So we can't have a transimpedance or, you know, something like that for L. L's got to be dimensionless. So this, just want to point out, this method, you know, is can be done with hand analysis. But you know, another nice thing about it, as I said, is it's pretty straightforward to do it in simulation too, as long as you take care to make sure that you don't disturb. You know, the tricky part is you have to all of this linear analysis that we're talking about is obviously all in small signal land, right? So all the quantities that we're talking about, the impedances, the voltage sources, and things like that, these are small signal quantities, right, in the linearized circuit. But in a real circuit that you're trying to simulate, obviously there's a bunch of bias voltages that are required just to put things at the appropriate operating point. So all that has to be maintained, right, undisturbed, while you're breaking the loop, injecting a test signal, and so on, right? So that's the only complication. But there's a few tricks for doing that you know, once you learn them, are not that earth-shattering. Basically, one common trick you'll see people use is to use a large value inductor to break the loop. So you've got, how should we draw this? Let's just do a simple case, right, of a unity gain buffer here. Okay, and now this, but let's say now that this op amp is going to be a real op amp like the ones in your assignment, right? So there's actually a schematic in there, a differential pair, some current mirrors, and all that stuff is actually in there. So, you know, you can't just go and connect this to ground over here. I said set all the independent sources to 0. But again, this is all in small signal land. So you set the small signal sources to 0. That small signal source may be probably, especially in a case like this, where I've powered the op amp from single-ended supply, VCC and ground, right? Probably the small signal applied there has to be superimposed on some bias voltage, right? There's a DC bias part, and then there's a small signal part on top of that. So these might be in SPICE, right? The DC part of a source and the AC part of a source, for example, right? So when you set the independent source to 0 here, you just set this to 0, okay? Which means you end up with this. You still have the DC bias applied. That's one. Now, let's say you're going to decide to break the loop here. Okay, it seems reasonable. The input impedance looking into the negative op-amp terminal is pretty high. There's a little bit of capacitance there, so maybe you could estimate that or something. But if I just break this, okay, and now I have to go and apply my test signal here. Right. Now if I just apply a small signal test signal, I've got a big problem because I've got a DC bias here of VI. So, you know, when you run the circuit simulation, the op-amp is going to have a large DC voltage, differential DC voltage applied. The output's just going to saturate. It's going to give you garbage, right? So you can't do that. Say, oh, okay, no problem. I'm going to just put the same VI here, right? And that'll fix it. Now I got the same VI and I just got a test signal. But turns out the op-amp has a little bit of offset in it, right? That's unavoidable because of the way the active load is connected, first stage or whatever, right? So there's a bit of offset in it. So you think you've done everything right, but because there's a DC offset of a couple millivolts in here, same thing happens. The output just goes right to the rails, right? And you still don't get the result you're after. You get garbage. So this is a very practical problem. It all looks good on paper when you draw this picture that's shown here in figure 11, but then you go and try it and you just keep getting garbage out and you don't know why. So you say, okay, well fine, now let me figure out what's the input offset, and you know, then I can adjust VI accordingly. You know, I find out the 2 millivolt input offset, so I make this VI plus 2 millivolts or whatever. So you could spend like an hour doing that, but you know, it's really fraught because if you try and run the simulation at a different temperature, boom, the offset's changed, right? And you're back at square one again. So instead, what's one approach to doing this is to say, okay, I want to, you know, when the real circuit, the thing is, this is all just an artifact of you trying to break the loop. Because when you go and connect this in, you know, the real world or in its actual use case, you've got closed loop. And in fact, the feedback takes care of the offset itself, right? It is the negative feedback establishes the exact voltage that's required at the negative op-amp terminal, assuming the loop's stable. It's going to establish the exact right voltage there so that the output is at a sort of nominal operating point and everything's good. So you kind of create this problem by breaking the loop, right? So the key is you want to break the loop at AC or at high frequency so that you can inject a little test signal, not even at high frequency, but at any frequencies that you're interested in. You want to be able to apply a small signal, but as far as the DC operating point analysis goes, you want everything shorted together. So that's why people insert a really big inductor here. It seems kind of silly, but you know, in a simulator, I mean, you can make this 1 Henry. You can make this 10 to the 3 Henries, right? There's no problem. There's no parasitics associated with it. It's just a device that you're inserting there to allow you to break the loop. Now you still want to stick in your test signal, right? But you know, you can't just go and do this, right? Because now you're kind of the test signal has, the way I've drawn it, has 0 DC part, so that's going to force the negative op-amp terminal to be at 0, or it's going to force the negative op-amp terminal to be at whatever the DC value that test source is. back in the same situation. You have to choose a perfect DC voltage and all that. So you can't do that. So instead, you would typically capacitively couple this input in with a huge capacitor. Okay. So, and you make those values large enough so that you know, you can even inject a 1 kilohertz test. You can even inject a 10 hertz test signal, or whatever is the lowest you need to go. That the capacitor still looks like a short. And it's a common mistake that I've saw a couple students every year that make it. That don't be shy with those values, because every year students do this and they say, "Well, you know, 1 Henry, that's ridiculous." They put like a microhenry there instead, and then they do the simulation and like, the response is all weird, and there's a high pass response to it. And it's because, right, obviously, if you go to a low enough frequency, you know, then that test signal is just shorted out by the inductor here, and it's the open circuit kicks in, and you've got nothing getting into the loop. So, you know, anyway, just don't be aware of what you're doing, right? But you know, don't be shy about that. Another method that I actually prefer, but it's a little bit dependent on the simulator you use. But I know in a lot of high-quality simulators, HSpice and so on, it's possible to use a resistor here. It's possible to have a resistor that has a different value of resistance for the DC operating point analysis and for the AC analysis. Okay, they're just different parameters for the same component. And that's really nice. Then you just say explicitly, okay, for the DC analysis, this thing has a resistance of 10 to the minus 10. For the AC analysis, this thing has a resistance of 10 to the 20. Okay, it's very clear. It's an open circuit for AC. It's a short circuit for DC analysis. And as you probably know, that all SPICE simulators do those two simulations totally separately. Basically, just like you're taught in undergrad. First, the simulator does the operating point analysis, figures out what all the DC voltages are, and then if you do an AC analysis, it linearizes everything first, and then runs the AC analysis, which is why it's so fast, because it's just a linear circuit, linear problem at that point. See, I forgot that. So you're right, because for the AC analysis, you've broken the loop. So let's go back to even for the resistor method I showed, your point is right on. Okay, so I'll stick with this for now. So what about, let's say, looking in here, you've got a capacitance CI, an input capacitance looking in there. Yeah, you should connect that here. Okay, that'd be part of the loop. Anything else you want to say about that? Now, some people, you know, if they're trying to be really, really accurate, they say, well, you know, the input capacitance looking into that op-amp terminal will vary if I want to do different process corner, slow corner, fast corner, if I want to change the temperature, like the biasing changes or something. In general, the gate capacitance of a transistor may change a little bit. And so then you know, if you want to analyze what happens to L here, in the presence of those kind of variations, then you need to take that into account, and you got to keep changing this sort of dummy load here, CI. It can be a bit of a pain. So you can either say, well, it's only changing by 10-20%, and anyway, it's a really high frequency pole anyway. That's one kind of approach, right? As you convince yourself it's no big deal somehow. Or if you're not sure about that, some people, basically what they do is they connect they make a whole nother copy of the same amplifier, just a direct copy of it, an exact duplicate that they just use as a load, right? And now you have to go and bias this thing exactly the same as the one up above and all that good stuff, right? But this is a little, you know, it's a bit of a rabbit hole, right? You start going down, well, you know, now I've got to make sure that, you know, maybe you want to make sure that load is not there for the DC analysis. So you've got to, you know, open it up for the DC analysis. You put your fancy resistor here or your huge cap. You know, it could go on and on and on. You make it more common. But just to point out as a general principle, sometimes the way people terminate the loop, which is easy to do in simulation, is just copy and paste, right? Whatever is actually connected there, you make an exact duplicate of it. Not so easy to do that in the lab all the time, but the simulator, you have all these tricks that you can pull. It's a bit of a, to me, it's a bit of a dirty solution. Obviously, it's going to slow down the simulation, but for the stuff we're doing in this course, it wouldn't be a big deal. 20 transistors instead of 10. Okay. And then since these are real transistors you have connected here, they'll vary with temperature and process in the exact same way as the real load does. Okay, so those are some nitty-gritty tricks that you may find useful. Here's just an example, right? If you're doing analysis, how breaking the loop at a convenient point can make it really trivial. Here again, by breaking the loop at the op-amp input, basically it's assumed to be a really high impedance, so I don't have to worry too much about terminating it, and the analysis falls out from there. And you see here's the final closed loop response. That's the ideal. Oops. The ideal closed loop gain, and then you've got L over 1 plus L, which is found from this analysis here. Oh, sorry, I should have drawn it the other way. So by the way, this method of finding L and then using L to infer what the closed loop response of the amplifier is itself a bit of an approximation. I mean, we didn't make any approximations when we did this analysis here. This is just some algebra here so that's obviously there's no approximation. This is exact as far as that goes. The approximation, the reason I say it's an approximation is because it was made implicitly just when we drew this picture. Specifically, we assumed that both A and beta were unilateral, which means that Y depends only on X and V depends only on Y, right? And there's no possible way that whatever is going on at X can somehow change V and work its way back through beta to affect Y. And basically, there's no reverse transmission around the loop at all. That's implicit just in drawing this picture, which is not quite the case. I mean, for example, take any amplifier, just to illustrate the point, right? Just consider a really simple common source amplifier here, which could be the equivalent half circuit of a differential pair, which is a very simple op-amp, right? So even for this, I mean, the normal small signal analysis we do would say that the gain, it's got a forward gain of GM times RDS, and then it's got some frequency response, maybe that depends on the Miller effect or whatever. But in fact, if we somehow injected a test signal here, let's say there was some noise or some other circuit was operating over there, there's all these capacitances here. So let's say there's CGD over here. Here's CGS. Maybe there's other capacitances connected there. So even, putting aside everything else, right away you've got just a passive voltage divider there. So that some fraction of the test signal at the output will appear at the input. Okay. So right there you see an example how there is some reverse transmission here. And that's not at all taken into account in this picture. And if you do take it into account, obviously the analysis gets more complicated, but you'll see that ACL is not simply A over 1 plus A beta. There'd be other terms there that depend on the reverse transmission. And our method, right? Our method for finding L doesn't, by breaking the loop, obviously, we somehow don't allow for certain kinds of reverse transmission to even show up in that simulation. So we're not going to cover that more general analysis in the course, but you can keep it in mind, especially in very high frequency circuits, RF circuits. Sometimes the more complete analysis is necessary because the parasitic reverse paths are significant and the forward gains are not that large. So that becomes more important. That's true. Usually we assume that beta is just, anyway, in this course we'll assume that beta is just a constant made up typically out of passive components, right? So either resistors or either only resistors or only capacitors that form a kind of a divider, current divider or voltage divider or something. So we assume that beta is less than 1 because it's just passive, or less than or equal to 1, I should say, right? And that it's just ratios of component values, so it's frequency dependent. Yeah. Okay. Here's another little bit more detailed analysis of a unity gain feedback with a very simple single stage op amp. So it's basically a differential pair with active load over here. And then the output stage is just a source follower, so it's not really a gain stage. That's why I would still consider this a single stage op amp. The second stage is just a buffer. And then you see the negative feedback connected back here. So here, right, one place we could break the loop would be here. Right? So this is very similar to the example I said. In terms of the analysis, we would, we've linearized the circuit and we have a small signal model here. So then we can follow the procedure a little bit straightforwardly, right? We can break the loop. We have to know what the input capacitance is, and we terminate the loop with that input capacitance, and we apply a test signal over here and look at the return voltage. It's all good. In practice, though, we have the problem I mentioned before, right? We have to be careful because obviously V in can't just be a small signal like that. It needs to be DC biased a little bit above ground, say about a volt above ground, in order to allow some voltage drop to appear across the current source, the tail current source, and also to allow for some VGS across Q1 so that the transistor is actually on. Right? So we need some bias voltage here, and there needs to be a corresponding bias voltage here. We need to, if we break the loop, we have to find some other way to establish all those bias voltages. So that's the discussion we already talked about. But here in this picture, it's just sort of a paper and pen exercise where we work on the linearized small signal circuit, and then everything, it's clear, right? What we need to do. Okay, so here's the picture that summarizes all that. Right, so the definition of the loop gain presupposes a linear system. So if we've got to simulate the loop, we've got to break the loop while still preserving the circuit's actual DC operating point. And so a lot of people use huge valued ideal inductors, right, to do that. And don't forget, you also need the large AC coupling capacitor here to introduce the input without disturbing the operating point. When you terminate the loop over here, even the way, it's not illustrated here, but sometimes even terminating the loop, you might have to be careful to not disturb the DC operating point. So it's fine if the impedance looking in here is purely capacitive, right? Because if it's purely capacitive, then you can terminate the loop with the same capacitance over here, and the capacitance won't disturb the operating point. It doesn't do anything to DC analysis. So it's fine. It can be there for the DC analysis. You don't have to worry. But if the impedance looking in here has a real part, has like a resistance, and then I just go and connect that resistance over here, again, even if only part of it is a resistance, that can disturb the DC operating point analysis too. And then you would want to put a big AC coupling cap in series with it so that it only looks like it's there and the AC analysis. But the DC analysis will just look like an open circuit. Even better, though, if you can, is to just choose to break the loop at a point where you don't have to worry about that. Usually you can do that. You can break the loop in a place where it's just a capacitance looking in, like a MOSFET gate or something.